I'm a game changer. I'm a risk taker.
Good morning, SCDF team Robo Turtles here.
The police have received a distress call of help for 3 civilians in a military reservoir. Apparently there has been a mild earthquake, which caused a huge tree to fall on top and trapped them underneath. One of them is in critical condition. Since the roads and pavements have been destroyed by the earthquake, we have 10 minutes to design hardware and code a robot to save the victim.
Roger that. Okay team, 𝗲𝗂𝐶𝗽𝗍𝗲, you work on the hardware, 𝗵𝗵 and 𝗟𝗑𝗧, you work on the software.
And Rebecca, you work on the hardware.
Rebecca, what should our wheels be like?
Let's use treads. No matter which point has the most friction, the robot will still be able to move because the point will lie on the treads, which is connected to the motor.
Yes, good point. Skid steer is not preferred as it heavily relies on the center of gravity. As the inclination of the robot changes when it moves on a ramp, the amount of weight being distributed to the driven wheels will change, and friction may not be sufficient to ensure rolling without slipping condition, thus causing skidding.
On the other hand, we do not have to worry about the undercarriage when using treads. Using 2 wheels with a cap in the middle results in a triangular-shaped gap. This is problematic when climbing up the ramp or overcoming the speed bump. The robot will have to make sure that the undercarriage is high enough to clear the speed bump due to the gap between the wheels. However, treads are level with the flat underside of the robot. As a result, the robot will not get stuck on the speed bump or the peak of the ramp.
Let's also shift the brain to be as front as possible to move the center of gravity closer to the color sensors for line tracking.
How should we position the color sensors?
Place them 1 cm above the ground so that it can overcome the speed bump. Also, space them out horizontally by the width of the line, which is about 2 cm. It is also placed as close to the wheels as possible so that the robot can track the line more tightly, especially at S-curves and 90-degree bands, which is prioritized over the angle the robot is hitting.
That's a wonderful consideration. And I was also thinking about choosing a level 2 evacuation point, which has walls of about 6 cm. Let's design a grab and lift claw for our robot as we need the claw to grab the victims and rescue kit and lift them into the sorting mechanism. We can open the claw to the width of the robot so that it can grab objects within a larger area to reduce the number of rounds the robot needs to make to sweep the entire evacuation zone. It is also in a wide V shape, so that the objects move towards the center of the robot when the robot moves forward, so that the object can be detected by the front color sensor.
Wait, where is the front color sensor?
The front color sensor is in the hole of the claw. It can accomplish multiple tasks, namely detection of obstacles, detection of rescue kit, and detection and distinguishing of live and dead victims. Therefore, these tasks only require 1 color sensor, which means they take up only 1 port, when the EV3 has only 4 ports.
Other than that, we should deposit the live victims before the dead ones at the evacuation point. See, we get more points. Let's separate the live and dead victims. After being determined by the color sensor whether the victim is alive or dead, the claw will grab the victim and place it on the sorting mechanism. The sorting mechanism will then tilt either left or right to place the victim in the respective deposit box.
What's a deposit box? Is it a compartment located on sides of the robot, slanting down backwards?
Yes. The angle of inclination of the deposit box has to be just right so that the victims will roll down using gravity, and the side of the box where the deposition occurs is not lower than 6 cm, which is the height of the rescue zone. On the side of the robot where the object enters is not too high for the sorting mechanism to sort the object. If the sorting mechanism is too high, the robot will need to be taller and the center of gravity would be too high, causing the robot to topple easily if climbing up the ramp. If the angle of inclination is too small, then the victims will not slide down the deposit box. But how should we deposit the object in the evacuation point?
Let's put a trigger which pushes against the walls of the evacuation point to release the victims from the deposit box. We should use gear ratio too, with the gear attached to the trigger larger than the gear attached to the barrier blocking the objects from depositing and ultimately releasing it. This is to make the barrier turn for 90 degrees when the trigger turns less for 50 degrees. This is because due to the low height of the evacuation point, the trigger cannot turn for 90 degrees, or it would contact the point at a weird angle, which makes it harder to push the trigger. Also, since the trigger turns in the opposite direction from the barrier, an even number of gears must be used. Let's use 2 gears.
Wonderful camaraderie hardware people. Now let's see what the software people have in store for us.
𝗟𝗧, how are we going to tackle line tracking?
I came across this intuitive method during my research, proportional integral and derivative, or PID line tracking. Taking the difference between the left and right color sensors values, otherwise known as the error, the robot should correct itself until the error is 0 so that both color sensors are sensing the same color. Multiplying this by proportional gain gives proportional. Integral is the sum of all errors since the robot starts line tracking, multiplied by integral gain. It corrects for steady state error, which will arise from pure proportional control. Derivative is the rate of change of error. It dampens the rate of oscillation which will arise from a high error. Adding proportional, integral, and derivative up, this gives the rate of turning of the robot.
But our left and right color sensors are not identical. as the reflectance values sensed by the color sensors are different when sensing the same color. Therefore, the robot would not be able to move straight and line breaks, as the values of white that the left and right color sensors sense are different, which results in a non-zero error.
Let's scale each sensor's values as a percentage of the minimum and maximum possible values each sensor could detect on the map, with the minimum being 0% and the maximum being 100%.
Great! For green squares, when both the sensors sense black, the robots will stop and move back a little to check for the presence of green squares. Based on the green squares, the robot turns accordingly. Despite this taking a longer time than sensing green squares directly and turning, the robot was more accurate as it had more time to align itself using PID to the black line. We had previously tried to sense green squares directly, but sometimes at double green squares, one sensor contacted the green square first, so the robot did not U-turn. Other times, the robot also detected green squares after the black line and turned mistakenly. We figured the best way to solve these problems while compromising speed is to sense the black line, then reverse to check for green squares.
The map also has a blue rescue kit, which we need to pick up and sort to the left deposit box, and an obstacle of a fixed dimension, which the robot needs to maneuver around. To differentiate between blue cube, obstacles, and nothingness, let's use the front color sensor, which would sense different reflectance values for different cases. Min, how should the robot know it is entering the evacuation zone?
Well, one of the sensors must sense red for the first time. To enter the evacuation zone exactly perpendicularly to the red line, the robot needs to align itself such that the color sensor sense exactly the same color. If the left color sensor senses more white than the right color sensor, the left color sensor is behind the line while the right color sensor is on the line. So, the robot should turn right on the spot such that both color sensors are on the line and vice versa.
After entering the evacuation zone, the robot should do blind sweeping, which is driving around the whole evacuation zone in a systematic way so as to cover the whole area of the evacuation zone. There are no lines for line tracking in the evacuation zone, so the robot needs to rely on wheel turning degrees to turn to a certain angle or move about. While this can be calibrated beforehand, there may be inaccuracies in turning due to physical and environmental factors outside of our control. Therefore, the robot needs to align to the boundaries, similar to how it aligns to a red line, so as to drive in parallel lines and sweep the area effectively.
During blind sweeping, the robot needs to collect victims the same way as the rescue kit. An open claw receives the victim, which will roll to the center as the robot moves. And the front color sensor will detect it and distinguish the color of the victim to turn the sorting mechanism accordingly, so that when the claw grabs and lifts the ball, it will fall into the correct deposit box.
For the evacuation point, while we considered using the front color sensor to sense it, we decided not to do that as it can be of any color, possibly the color of the victims. To reduce hard-coding the different colors and from mixing the point with the victim, we decided to use the distance traveled by wheels to know whether the robot is in contact with the point. For instance, without the point, the robot should reach the boundaries and hence run at least a certain pre-calibrated distance. However, if the robot fails to see the boundaries after driving that distance, it will mean the robot is ramming against the point.
And here's how the robot should deposit the victims in the right order and the blue cube through hard coding.
Next, to find the exit, let's input the color of the exit line beforehand. During blind sweeping, the robot will have come into contact with the exit and stop its position. Using hard coding, the robot will maneuver itself to the exit line from the deposit zone.
That's so amazing! How perfect it is!
Well, there are areas of imperfections. For obstacle avoidance, we might encounter variable obstacles. We will improve by letting the robot line track around the obstacle using an ultrasonic or time-of-flight sensor mounted to one side of the robot. We will set a threshold value, which is how far the robot should be away from the obstacle. While maneuvering its way around the obstacle, if the distance detected by the sensor falls below the threshold value, the robot will need to turn less urgently to avoid collision with the obstacle. If that distance falls above the threshold value, the robot will need to turn more urgently to correct itself so that it does not stray too far away from the obstacle and can return to the line after the obstacle as soon as possible. Doing this will reduce hard coding for different dimensions of obstacles.
Congratulations, you have successfully solved the mission. Through this mission, you have honed your robotics and physics skills to come out with a working robot. Thanks to you, the 2 live victims are recovering well, but of course one remains dead and is not eaten by snakes due to your prompt rescue. Through this, you have learned about the theory, center of gravity, turning facts of fossils, satisfying your hunger to learn. But above all, you have learned the importance of teamwork and perseverance. which is not giving up when obstacles are in your way.
Today we honor Team RoboTurtles as one of the greatest roboticians of our time.